This is the second video for Chapter 9 from the McGraw-Hill book. We're talking about types of reactions. Now, yesterday, or on the first set of notes, we introduced the types just as a survey. We're going to go into a little bit more depth today, and you need to know what the types of reactions are, and you need to be able to predict based on, okay, this is a synthesis reaction, I know what the products are going to look like. That's important because a little over half the reactions that you get on the quiz and the test and that you'll see on the review and for the rest of the year will give you the left side of the equation, the reactants, and say complete this and balance. So it's important to know the types of reactions. So the first reaction is called a synthesis, and there are really three names for this: synthesis, combination, and composition. So if you see any of those, you'll recognize that it's this same type of reaction. How do we recognize it? One product. Okay. Now, there are more complex cases of synthesis reactions where there's some other things going on, and maybe you have a double replacement and synthesis. But for us, our synthesis are going to have one product. So if you see one product, automatically you know it's synthesis. The other way to predict this is what if we see two elements with a plus in between? Well, the only thing that you can do with two elements with a plus in between is add them together, and that gives one product. So either one of those is a giveaway that you're going to have a synthesis reaction. Possibly could be two compounds. Now, I've told most of my classes that if you look at the PowerPoint, the first practice page and your review, and also in the book, I think you'll see about 5 of these synthesis reactions, maybe 6, that are two compounds added together. I'm going to pull one of those 5 or 6 and put it on the test. Just be a little bit more difficult, a little more challenging synthesis reaction, maybe separate the 100s from the 90s. Here are 2 of them. How do we do these? Well, first of all, if the one product is not a molecular compound, then if it is a molecular compound, I'm going to give you the name of it underneath the blank. Why? Because it's real hard to predict what kind of molecular compound will pop up. If it's an ionic compound, it's a lot easier to predict because you know there is a plus ion and a minus ion, and that helps you predict. So let's look at this first one. CaO plus H2O yields blank. And this is probably how you'll see this one if you get this one. So the first item is to say, all right, there's no name underneath it, so I know it's ionic. Since it's ionic, there's going to be a plus ion and a minus ion. So you'll know at that point that you could find the plus ion from what you have here. Well, we'll look at what we have. The only element that has to produce a positive ion is calcium, because for y'all, all the metals we've dealt with always make positive ions. So calcium is the positive ion, Ca. What we have left is O and H. What polyatomic ion for the second spot has a negative charge and has O and H? Well, look at your polyatomic ion chart. There is only one, OH, hydroxide. So calcium has a 2 charge. That gives us a 2 for the OH and a 1 for the calcium. And we're balanced. We're done. And that's a synthesis that involves 2 compounds. So you will get one of those on the quiz and the test. Make sure that you look over those, are familiar with, one, how you predict what the product's going to be. And if you look over the 4 or 5 or 6 that are available between the book, that practice page, it's the first practice page, the one that has the composition, reaction, decomposition. It's got the 4 or 5 different categories with 4 or 5 reactions each. So look over those, and probably going to pull 4 or 5 of the reactions from that particular page, that practice page, and then some from the review. Some of them are on both the review and that practice page. So there we go. The other one, SO3 plus H2O, again, same way. what is the only ion that could be positive here? We know we have one product. It's not molecular because I didn't name it. So the only thing you have that could be positive, the positive ion, is H. S is above the stair step, makes a -2 ion. O, above the stair step, makes a -2 ion. SO3 and SO4 are both -2 ions. So there is only one choice for the positive. So if you work your way through this, logically, you'll see the H is there. And the best choice for the other side will be SO4 because we have 4 oxygens. SO3 plus 1 is SO4. When we plug that in, we cross the 2 down, the 1 over here, H2SO4, it's balanced, and we're done. So look over those. Make sure that you know how to do those tougher combinations with compounds because you'll see at least one of those. So we'll move on. The next type of reaction is decomposition, and it's the opposite of composition, combination, or synthesis. So obviously if combination has one product, and this is the opposite, decomposition has one reactant. So if you see one reactant and an arrow, it's decomposition. So it really isn't all that challenging to identify the types. Now, for most of these, if you have something like NaCl and it decomposes they just have that, you know it decomposes into two things. Well, it's going to be Na and Cl2. Cl2 is a gas, Na is a solid, and then we just balance it. Okay, 2, 2, we're done. So the ones with just 2 elements are really not going to be that challenging. There is one that's a little more challenging, and I'll tell you right now, you will have a carbonate decomposition. Not that bad. Carbonate is a metal with CO3, and they usually decompose with heat. The little triangle means heat. They always break into at least 2 parts, and one of the parts is CO2. So if we subtract the C and 2 of the O's from this, we're left with CaO. And that's the pattern for carbonates. They break into the metal with oxygen plus CO2. And even if it's 1 from 1A, Na2CO3, okay, remember this is a 2, this is a 1, so when we crisscross we get Na2CO3. All of the metals in 1A follow this pattern. All of the metals in 2A follow that pattern. So you may not get these same metals, but you're going to get one from 1A or 2A. I can promise you that. So this will break into Na2O. Oxygen's got a 2, Na's got a 1, plus CO2. Okay, so those are your decomposition. We'll move on. Combustion. You know, combustion, I've talked to teachers before that consider combustion to be the hardest. I consider it to be the easiest. And the reason is that, and people have shown this over the years that I've taught, that once I show them the pattern, it's something predictable. You know what's going to happen. You know how to balance it. They don't turn out to be all so bad. There are 2 main types of combustion when we're talking about carbon combustion, carbon compound combustion. I will give you a carbon compound, something like CH4, or it may even be a carbohydrate, something with oxygen, but it's going to have at least carbon and hydrogen in it, plus O2 yields CO2 plus H2O. Okay, how do we remember that? Well, the easiest way to remember combustion is like this. What does all that mean? Well, so every combustion has to have oxygen or it doesn't occur. So the breathing in, that represents oxygen. We breathe in to take in air, which the ingredient we need in air is oxygen. And then breathe out. If you get a chance, get a piece of glass or glass, like this glass apple. When I breathe out, it's hard to see probably, but you could probably see that there was moisture condensation on the apple. It's condensation, and when we mark it, you can see that we wipe off the moisture. That is H2O. When we breathe out H2O. We also breathe out CO2. So there you go. That's your reaction. We eat some carbon compound, breathe in oxygen, and out CO2 and H2O. Incomplete combustion. It's the same thing except it's CO on the product side. Same template, just CO2 for complete, CO for incomplete. So that makes it easy. The other kind of combustion, one that we will see, is combustion of hydrogen. And since there's no carbon, there can be no CO2. What's the only other product? H2O. Combustion of hydrogen produces H2O as a product. So H2 plus O2 yields H2O is the skeleton equation for combustion of hydrogen. So those are the three types of combustion that you'd see. And it's really the only combustion that could also be called a synthesis, because you're adding two things together to get one product. All right, so we move on. In balancing combustion, so let's do one real quick. So we've got C2H6 plus O2 yields CO2 plus H2O. There's a pattern. Balance the hard stuff first, balance the oxygen last, because it's by itself. We can make it anything we want. 2 carbons, put a 2 in front of the C. Carbons are now balanced. 6 hydrogens, put a 3 in front of the H2, because 3 times 2 H's is 6. The carbon and hydrogen is balanced. All we've got left is to balance the oxygen. And even if it's odd number of oxygen, we can balance it. There's a trick to make an O2 into an odd number. So we've got 2 times 2, that's 4 oxygens. And we've got 3 times 1, that's 3. We need 7 oxygens. How do we do that? 2 times 3.5 equals 7. And most of you would say, well, wait a minute, can we do that? Sure you can. We've just balanced the equation. Now, in most cases, you don't want to leave it as a decimal. How do we fix a 0.5 decimal? We double it. You can't double one without doubling them all, because they all have to be the same ratios. So instead of 1, we have 2, C2H6. 3.5 becomes 7. 2 becomes 4. 3 becomes 6. It's the most reduced form, and it's balanced. That's a little trick that you can use to balance any combustion problem. And they really come out pretty easily. Now, the only trick, the thing that you need to be careful of, the tricky ones, have carbohydrates, which would be carbon, hydrogen, and oxygen. Don't forget to count the oxygen that's in your fuel over here and the O2 oxygen, if you have one of those that has a carbohydrate. Other than that, you know, the combustions aren't that bad. All right, single replacement. The last 2 types of reactions that we have are replacement reactions. Single replacement, how do we recognize that? Well, it has one element and a compound. So we've got an element like Mg plus HCl. So if you have an element and an ionic compound, an acid or water, probably single replacement. And we've got a couple of types of single replacements, but one of them uses the activity series of metal. So the activity series is in your book, also be on your possibly useful page. And the activity series is a list of metals in order from the strongest to the weakest. And we have to look at it to figure out, does the reaction happen? We look at our activity series, we see magnesium is number 4 or 5, and hydrogen is down below the middle. So magnesium's higher. You're going to draw a line after the first capital letter in the compound. The metal will compete with the first element in the compound. In this case, magnesium kicks hydrogen out. And hydrogen, now we're going to have Mg with Cl, and we crisscross that and get MgCl2 plus H2. Remember, the H2 is H2 because hydrogen is one of the diatomics. It doesn't sit by itself as H. It has to be H2. And then we balance it. 2 H's, 2 Cl's, we put a 2 in front of the HCl. That's single replacement. What if the element is not higher than the metal in the compound? Well, here's H2 plus MgCl2. Now we're going to look at this and say, all right, H is not above magnesium, so we draw a line after Mg and we say H and Mg are battling here. H is not strong enough to kick it out because it's weaker, it's below it. No reaction in our and you're done. Okay? So there's one other thing that's important, and on all of your activity series charts, especially the one that you get on the quiz and the test, it will tell you at the bottom that the top four, sodium through lithium, in most cases, it depends on which chart. This one's a little shorter chart. It doesn't even have lithium on it. But so it'll tell you the top four will take H's, hydrogens, from any compound, including water. But anything weaker than those top four can only take H's from acids. So this is important if you have something like water. Draw a line after the first capital, and that leaves hydrogen, Fe, and hydrogen. Now you look at it and say, okay, iron is above hydrogen, so it should take the hydrogen's place, but it's not strong enough to break this hydrogen bonding and steal that H. So make sure you pay special attention to that little statement next to your activity series. You don't have to memorize it. It tells you right there. It says which ones will take H's from water and which ones won't. And this would be no reaction. And I think maybe you have that on your review. Maybe I put that one on the quiz. So, make sure that you're aware of that, because there will be at least one no reaction on the quiz or the test. You need to make sure that you're up on why there's no reaction. Okay, so that's not the only type of single replacement. The other type of single replacement involves halogens. So you're not going to get a chart of halogens on the possibly useful page because you already have it. The periodic table has the halogens in order of their strength. And these are the four. So when you see two of those in the same reactants, you're probably going to be suspicious that this is going to be a halogen single replacement. What does it look like? Well, it'll be like Cl2 gas plus HBr. So you have your compound, which is, like I said, either an acid, water, or ionic compound, and you have a single element. But in this case, when you draw a line after the first capital letter, you don't have two items on the activity series chart. You have two halogens, and they're fighting for the negative or anion position. How do we figure out which one's stronger? Look at the periodic table. Fluorine's the strongest, then chlorine, then bromine, then iodine, and those four in order. And those are the only four I'm going to give you for this alternate type of single replacement. Cl is stronger than Br, so it takes the hydrogen, and we end up with Br getting kicked out. And we have Br gas. So there's two Brs. We need to put a 2 there and a 2 there, and that gives us two Cls, and then we're balanced. So that's the other type of single replacement. Single replacement is the only thing that uses the activity series chart, not double replacement. There's a question on the test that will ask you about how do we decide if double replacements occur. One of the choices is look at the activity series chart. Not right. Okay, so there's 3 rules we're going to talk about with double replacement, and that's the next type of reaction. So what is double replacement? It is the only type of reaction that you're going to see that only has 2 ionic compounds on the left side. Now, for reactants. So there's going to be 2 ionic compounds. Let's use MgOH2, okay, 1 and 2 crisscross to make MgOH2 plus HCl. So we have 2 ionic compounds on the left. Chances are really good it's going to be a double replacement. Now, when I say ionic, keep in mind that some acids are really just very polar molecular, but acids function like ionic compounds for this case. So we draw a line after the first capital letter, and including the whole symbol, and that would be Mg and H. Mg and H, we do not look at the activity series of metals. On the test, I've got a little statement in the instructions. It says consider all double replacements to occur. Okay, because I'm going to give you some that do occur. Then I'm going to ask you a question about why do they occur, and we're going to go over that here in a second. So the Mg and the H just swap places. The first partners, kind of like 2 partners at 2 couples in a dance. They swap the male partners from one couple to the other, and like tap them on the back and say, can I switch partners here? And that's what happens. The Mg is now with the Cl. We get MgCl2. Make sure you crisscross when you make new ionic compounds. You have to reform the new compound with the subnumbers. You don't take the Cl1 subnumber across, you re-crisscross and make a new subnumber. Plus HOH. So we don't take the 2 subnumber with the H because H and OH both have 1, and we end up with HOH, which is water, and MgCl2. 2 Cl's, we put a 2 there. That gives us 2 H's, so we need to put a 2 in front of the HOH, and that gives us 2 OH's, but we're balanced. So draw a line after the first capital letter, swap the first 2 partners, and re-crisscross on your new products, and then balance. That's double replacement. Now, there are 3 things that cause double replacement to want to occur. One is that water is a product, which is what we had happen here. HOH, H2O is a product, the reaction will occur. The other 2, if a gas, up arrow or a little G in the products occurs, or if a precipitate occurs. Y'all remember the reaction we did in lab where we mixed 2 chemicals together, lead 2 nitrate and potassium iodide. It made the yellow lead iodide. That was a precipitate which made the reaction go. So remember those 3 things because I'll ask you that question. What are the 3 driving forces for double replacement? Precipitate, a gas, either of those formed, or water formed as a product. Okay, so those are the types of reactions. We're done. There will be 2 more pages that we have for the last set of notes. Go really quick. We're going to talk about ionic equations, but for the most part, we're done. Do lots of practice on those pages. Especially get your review done first, and then work on the practice page that has the different sections, the composition, the decomposition, single replacement, double replacement, combustion, because that one is probably the best practice for the quiz. You've got 3 or 4 choices of practice pages. Do as much as you can, but don't just spend like 10 or 12 hours working problems. If you kind of be selective and make sure your review's done and maybe do one of the practice pages and then pick and choose problems that you need more work on. Work hard, good luck, and we will see you in class.